Let's see if we finish today the pipe systems material, and then we would be able to, well, actually, what do we do next? We do an exam next. That's what we do, right? That's what we do on Monday. And then on Wednesday, we do the CFD class that I delayed for you to have the material available for the third lab, which probably should be scheduled very soon. So, okay. At the end of last class, what we did was one example of pipe flow, the one from Moody's 1944 famous paper. But that is just one type of 3 different sorts of problems that you can encounter for pipe flow. And these are, first of all, we assume that the fluid is always given. So we always know what type of fluid we're trying to move about inside a pipe system. We know its viscosity, density, and so on. So the fluid is always given. And we will have problems of type 1 are determining the pressure drop, and or head loss. And that's going to be given a desired flow rate, or velocity, and for a given geometry. So basically, this is what we've already done in the example from last lecture. And this can be called the head loss problem. So that's the problem we already have solved the previous class, but there's another possibility, is that what if we actually want to determine the flow rate for a given pressure difference? Suppose that you have already a pump that you know that is going to give you so much of a pressure capacity, or perhaps it's a pressure-driven flow. The flow is driven by some elevation change, and so that's what you have. So you have to work with a given amount of pressure drop, and you want to know how much fluid you're going to be able to move. That's the second type. When you're constrained by your driving force, which is the pressure difference. And also for a given geometry. This is the second type, determine the flow rate. So let's just call it the flow rate problem. And the third type of problem that you can have for pipe flow systems is to determine the pipe diameter. Given that, the pipe diameter that you would need to achieve a certain pressure drop in the system, again, because perhaps you have a fixed budget of energy, say, for the system, right? So you have to cap how much power is required from the pump And so you want to size the diameter of the pipe accordingly to that constraint. That's another possibility. So that's given pressure drop and flow rate. So we can call this a sizing problem. We want to determine the pipe diameter. That makes sense? Now, problem 1, as you saw last lecture, is quite easy to solve. We just go into the Moody chart, or if you have a little program that uses one of the empirical formulas that approximates the Moody chart, then you can get out of there the friction factor with your velocity and so on, calculate your Reynolds number for the given geometry and velocity, and you get your pressure drop. You calculate your pressure drop. That's quite easy, but not so for problems type 2 and 3. For problems type 2 and 3, actually, we are going to require some sort of iterative procedure. It's not right direct from the Moody chart. So we're going to do a couple of examples. To illustrate. Type 1 is easy. Type 2 and 3 require an iterative procedure. So they're not so easy. Of course, one can write a computer program to make this easier. But let's do an example by hand to illustrate how this would work. Here's one example. We have, in this example, a tank of water, and we consider water flowing from this tank through you see here, it's a 50 centimeter diameter pipe. So diameter of the pipe is 50 centimeters. And this is commercial steel. And so for commercial steel, you can go inside a handbook or some spec sheets or a table or whatever, and you can get for commercial steel the value of the roughness. We get epsilon, the roughness, equal to 0.046 millimeters. The length of the pipe system is 100 meters. We're given an elevation of 40 and an elevation here of 60 from the top of the tank to the pipe center line. And so let's call this, we got a 1 here, so let's call that Z1 equals to 60 meters and Z2 equal to 40 meters. So you see this is a gravity driven, driven by the elevation difference, the flow. And we're told it's water, so we can get the viscosity of water. From a table, and I've got it right here. Nu is 10 to the minus 6 meters squared per second. And we're asked, of course, to determine the flow rate. So this is going to be a second type problem, type 2. Determine the flow rate. I'm going to make that picture disappear now. If you've got it all, not yet, okay. Because then I have a little bit more of space to solve the problem. Pretty sure that I've got it to disappear, yes. Back, there you are. Ready? Okay, so here is all the data for the problem, and the question is, what is the flow rate? A flow rate problem type 2. We're going to assume that it's a fully developed turbulent flow. And we note that there is no direct way at this point of using the Moody diagram, the Moody chart, right? Because we don't know the velocity, so we can't calculate the Reynolds number. And so what do we do? Any ideas? How?
So
Close. Bernoulli's equation, remember, is for ideal flow, so there wouldn't be any head loss, right? Because it's ideal, totally ideal. Energy equation, excellent. Very good. So we use our energy equation between points 1 and 2, and that will allow us to get the head loss, as you very well suggested. Okay? So energy equation between points 1 and 2 in our system. And so we have P1 over gamma plus V1 squared over 2G. So in terms of head loss, the energy equation in the head loss form, plus Z1 equals P2 over gamma plus V2 squared over 2G plus Z2. There are no pumps or turbines in the system, and so we just have the head loss. And this is what we want to determine. What do we have? We have point 1 was at the top of in the surface of the reservoir. We assume there's a very big reservoir and the velocity is approximately 0 there. So velocity at 1 is 0. This is atmospheric. At point 2, which was in the exit of the pipe, if you noticed in the picture, let me bring it back again. You can barely see it there behind my annotations, but you see that point 2 is at the exit of the pipe. Okay? So we also have atmospheric pressure. Z1 and Z2 are given. So we've got 60 is equal to V2, we don't know unfortunately, over 2G plus 40 plus the head loss. For the head loss, we can use our formula for head loss, which depends on the friction factor. We don't know the friction factor. Normally we would get it from the Moody chart, but we don't know it at this point. So let's just write F L over D V2 squared over 2G. And you see here that you have two unknowns, but you can express the velocity in terms of the friction factor. I'm trying to use my real estate here cleverly to solve most of the problem, but it's not going to fit anyway. V, I could get V, so I'm simplifying things out here. And we have 60 minus 40, that's 20, and so on. So I'll just write it out here. 20 times 2G divided by 1, and L over D is 200 F, and it's to the power 1/2. So here we have an expression of velocity depending on the friction factor. So any ideas what the next step could be? Any guess? Okay, that gives us the roughness. But we don't have Reynolds number, so we can't go in the Moody chart. Take a guess. That's what we do. We make a guess. I was trying to tell you the answer and nobody got it. Take a guess. So that's what we do. We guess, and with that guess, get the velocity, then get the Reynolds number, put it in the Moody chart, get F, and if it's not correct, we guess again. We do it again. That's the way. Let's yes. Let's try. P1 was at the top of the reservoir. Yeah. So it's so we do a trial solution by guessing F, guess F, then find V, calculate Reynolds, and then we can go on the Moody chart. Anybody remember what we got? You got the number last time of the problem that we did last class. Anybody remember what we got that time for the F? 0.02. Let's try that. We just did a problem and we got that. So let's try. Say F suppose is 0.02. So we go on and calculate the velocity. Everybody have a calculator? Did I make a mistake in the equation? 200? It's 100. So 50 centimeters is equal to 0.5 meters. And so L over D is 2 times 100. That's 200. That's better. Okay. Actually, I have 8.86. Do you think you approximated correctly? Okay. Maybe I didn't. Okay, 8.85. Okay, good. 8.85 meters per second. So now, calculate Reynolds number. Reynolds equals V times D over nu. We have D, 0.5 meters, divided by nu, which is already here. $4 million. So 4 times 10 to the 6. 4, what are the two decimal? Just give me 2 decimal points after the 4. 4.3. 4.43 times 10 to the 6. Well, we are at least satisfied that it's definitely turbulent. So our assumption that it was turbulent from the beginning is fine. We remember to check that just in case. It should be. So now what do? We use this trial solution in the Moody diagram. And we need to get the roughness, the relative roughness, epsilon over D. Epsilon is 0.046 millimeters, so 0.046 times 10 to the minus 3 meters divided by 0.5. And I've got the answer right here, 9.2 times 10 to the minus 5. So we've got everything to go on the Moody chart. Anybody want to try that? Actually, for this one, you know, it's 9 times 10 to the minus 5. You're not going to be able to find that in there, so let's just approximate upwards to 1 times 10 to the minus 4. So basically 9 is close to 10, right? So it's just approximately 10 to the minus 4, and then you can go in the Moody chart, right? Got that? So now we have Reynolds 4 times 10 to the 6. Relative roughness 10 to the minus 4. And you can go on the Moody chart. You don't get it? Okay, let me...
No, I understand I do, but I'm saying it's not right. It's not right.
Something's not right? Oh, the F wasn't right.
Yeah.
Okay. What do you get for F?
Point
I kind of approximated to 0.012 in my
okay.
sort of
So
a little, you know, I mean, we're reading from the plot sort of.
Right.
Okay, so we get F more or less 0.012. So now recalculate VIG, recalculate Reynolds number, go back on the Moody diagram and see what comes out. Care to try that? You want to give me a new velocity? With 0.012? Back here? Or maybe over here. I got some new calculator. Velocity, what? Velocity is 10.7. Okay, so 10.7. The F is 0.012. So we get 10.7. The new Reynolds number is, what's the new Reynolds number? Ten to the 6. Okay. So now we can go again in the Moody diagram because we have the same value of relative roughness. Only the Reynolds number basically went up a bit. And what do you get? In order to satisfy, no, the friction factor that we chose, we chose one completely at random. It was just a wild guess. And we calculated everything and we obtained something smaller. So we need to recalculate velocity and everything, go back in the Moody chart and see what comes out. I actually got the same value about 0.012. I find that it doesn't change, and at this point, basically you're getting, if you're not getting any change on it, then that's when you stop. So basically, very quickly, what I wanted to say is even if you start with a sort of a good guess, reasonable guess, very quickly you close in on the right value. So you would have saved a little bit of work, true, but you would have still had to do it twice to confirm. And so, yeah, and basically at this, we had one guess, we had to do the calculation twice to be sure that that one was a good value, the 0.012.
I don't understand the use of the trial because if you're putting in the F as 0.012, shouldn't you just get that back out anyway?
Yeah. But we didn't choose 0.012, we choose 0.02 just out of the, you know, it's just a guess.
So when we look back in the Moody chart, we were just verifying what we had already seen.
But you need to, you know, calculate it twice to see that it doesn't change and decide that that's the value you're going to keep.
You're creating an outlier for verification.
No, you start with a guess, which could be good or could be not so good. I'm demonstrating here that with a guess that was not so good, you still get a converged result after 2 iterations.
So you only have to go through this twice?
Yes. Not always. You can't really write down a law that says, you know, you're only going to do it twice. You need to confirm that your solution didn't change.
If we use the F equals 0.012 and we went through the whole thing and it gave us back a different F, how was that?
You would have to do it again until it converges. You see? But if you had started with 0.012 in this problem, you would have gotten 0.012 the second time around, and then you stop. Within the accuracy of the Moody chart, because basically you're always reading from a chart, and so it's the nearest line. You get the nearest grid point on your plot, And more accuracy than that you're never going to get.
So what's the accuracy?
It's already the accuracy of the Moody chart, as we said last time, is plus or minus 5% on turbulent flow case, I think it was, or plus or minus 5% for smooth pipes, and I don't remember exactly. 10% for the cases of more rough pipes. Yeah. So. Yeah, that's all. But it converges rather quickly anyway. It converges rather quickly is what I'm trying to show. Yeah. We converge to the solution by the iterative procedure and stop. So now there's no need for another iteration, and once F is unchanged, and now we can calculate the flow rate because we have the velocity. So remember there was an extra step which is calculating the flow rate. So we need to multiply by the area to get Q. Q equals V times A. And just to finish with our results, Q equals V times A, and that is, what is it, 10.7 meters per second times pi over 4 times diameter squared, and I get 2.1 meters cubed divided by second. Okay? All right, so let's do problem type number 3 now. The sizing problem. So in this case, the problem is written here. You have to decide on the diameter of a pipe, which is going to be asphalted cast iron pipe, which is needed to carry 3 cubic feet per second for whatever application you require that amount of water, 3 cubic feet per second at 60 degrees Fahrenheit, so you can get your viscosity, and with a head loss of 4 feet per 1,000 feet of length.
CFS cubic feet per second.
Cubic feet per second, yes. So again, an iterative method is going to be required because F is actually a function of diameter. So we need to use an iterative method to solve this. And we have to look up the roughness of asphalted cast iron. And we find epsilon from some table or a handbook. What have I got here? Where is it? Oh, here it is. 0, I think it was on our previous example, wasn't it? 0.0004 feet. The one from Moody. We have Q equals 3 cubic feet per second, and we have water at 6 degrees, so we can get the viscosity in the appropriate units. 1.22 times 10 to the minus 5 feet squared divided by second. Alright, so the first thing that we have is, well, we need an expression for the diameter to iterate with, right? We don't have that yet. So let's see, what do we know? We know that the head loss is equal to the friction factor F times L over D times V squared over 2G. And the velocity is going to depend on the given flow rate, Q. So we need to kind of plug that in. F, L over D. And for velocity, we put Q divided by A. So q squared divided by a squared is the velocity squared. And we can put now the area, so friction factor L q squared divided by 2g, and the area is pi over 4. And let's put pi over 4 squared, and we have diameter squared, right? So diameter to the power 4 plus 1 diameter, that's 5, right? Because there's one already here. So we have 5 diameters. Multiple, okay? Everybody clear with that? Sound good. So now d to the power 5 is equal to f L q squared divided by, well, let's approximate all this number and just put some numeric value here to start working this out. I have 785 squared and 2GHL. Why did I leave the 2 in there? I don't know. Let's just. Now we have we can start with a trial solution. Guess F, get D. Then once we get D, we can get Reynolds and relative roughness. Everything depends on D now. And go back to the Moody chart. So trial solution again. In this case, guess F, get D, find Reynolds and relative roughness, and then go on the Moody chart. So I have as a suggestion F equals 0.015. For that case, let me write down what D would be so that somebody can plug it in the calculator. D to the power 5 would be 0.015 times, what's the length? 1,000 feet times q squared. Q is 3 feet per second, cubic feet per second, and all of these squared. And I have pi over 4 squared already as a number over here, 0.785 squared, and gravity times 2g, 64.4 feet per second squared. And what else is there? We want 4 feet, right, of head loss. So that's the formula for diameter to the power 5. So you have to take the 5th square root. Yes?
What is the 4 feet per 1,000 feet? Like, how do we deal with that?
We put 4 and 1,000. In 1,000 length,
Okay, so
you have 4 feet.
that's a double of that.
Yes. And we have it upside down. You know, we have the inverse in the formula. So did you calculate it? You got D? What did you get for D? 0.968 I have here. Right, good. That's what I got. And now we get Reynolds. Oh, no, sorry. Other way around. V times D over nu. Oh, but we need V. So we need to get V from... So this one is a little bit more cumbersome, isn't it? But need V from How do we get it? V equals Q divided by area. Q is 3 feet per cubic feet per second. 3 is given. The area, we do have the diameter now, so divided by pi over 4 diameter squared. And just the answer is 4.08 feet per second. Now we can get Reynolds. 4.08 feet per second. All along, of course, of the calculation, if you are thorough, you should carry your units to make sure that it all makes sense and you haven't made an algebraic mistake. That was our first tip to do better on exams. That's the diameter. Nu 1.22 times 10 to the minus 5 feet squared over second. What do you get? You have it? Three, 10 to the fifth, okay. Good. It is definitely turbulent. And now we have epsilon over d. It's given. No, it's not given, but we can calculate it from the diameter. 0.0004 divided by 0.968. And actually, it doesn't change very much. We can keep 0.004 to go on the Moody chart. So now Moody diagram gives you a new F. According to my notes and revision of this is 0.018. With this new F, we get a new D, new V, new Reynolds, new E over epsilon over D, everything again, and get a new F. According to my calculations that I've done before, when you do that one more time, you're going to get the same F. So it converges on the second iteration again. Solution is converged, and the diameter that I get with this value of F here is, so the new D is 1.002 feet. New velocity is about 3.81 feet per second. New Reynolds is not, it doesn't change very much. And you go back on the Moody chart and get the same F equals 0.018, and the solution is converged. But then you have to realize that this value of D, you actually have to go and choose something that's commercially available. So you need to choose the closest value that is being manufactured. Probably is going to be 1 foot, right? You can't just order piping from any diameter that you choose. There's going to be very fixed values that are available commercially. Yes?
So it seems like the first trial, pick an F and find the F. And that F that we found, that's not the same as the F that we chose. You use that same F in the other trial.
Yes. That's the concept of an iterative procedure. You pick a guess, carry it out all the way to get a solution, and then that changes your guess and you get a new guess. You calculate everything again. Yes. And this can be done several times, and the solution converges very quickly in this case. So we need to specify a diameter that's commercially available, of course, in the end. So that's the end of the result. So another, of course, option is to have used one of the formulas that's available, or you can then write a little computer program and then everything would be, nowadays you would write a little computer program, right, instead of doing everything by hand. But this is the this is where this, right? And many, if you're working in a company that does this all the time, you will have a system, computerized system that will simplify, make all of these easier. But this is the way it works. Okay, let's take a little break.